This video was produced by Virginia View, a consortium dedicated to promoting remote sensing outreach, education, and research through funding by the America View Consortium. This video was developed in partnership with the Virginia Geospatial Extension Program and GeoTED UAS. Its contents are solely the responsibility of the authors and do not necessarily represent the official views of America View, the USGS, or other partners. The mention of trade names or commercial products does not constitute their endorsement. Recall from Chapter 17, where we covered radiometric enhancement, that a histogram depicts the distribution of the number of pixels with respect to pixel values. We now need to evaluate pixel values within training data to assess their degree of normality. If pixel values within any one of the classes are not normally distributed, for example, they display a bimodal histogram, it's likely that a specific class has not been sufficiently trained. If this is the case, additional training samples are needed to cover missing spectral values. To create a histogram, we'll use the training sample file we created in Part 2 where we analyzed scatter plots, the one that collapsed all individual samples into one training sample for each class. In order to create a histogram for training samples, we need to extract the pixel values for all bands of the composite image into a separate raster file for each informational class. We'll be using the raster functions procedure demonstrated in Chapter 15. Let's clip the Landsat image by a feature from the training sample. To select an individual feature from a vector feature class, go to Map, Select, then select one of the forest polygons in the map viewer. This selects all of the forest features because we collapsed all of the separate training samples for forest into one when we started working with scatterplot. Now select the composite image in Contents, go to the Imagery tab and Raster Functions. Find the Data Management tools and select Clip. Set your parameters with the Landsat 8 image as the input raster, the training samples for the clipping geometry, use the Input Features checkbox, and under General give it a new name and set the output pixel type to 16-bit unsigned. Now let's create new layer. If you check the properties of the new layer, you'll find that it's an 11-band composite image as we expect. Turn off all layers except for Clip Forest. The 11-band composite image has been clipped to the extent of each of the forest training sample polygons. Set the band combination for this new layer to color infrared or 543. Be sure the new layer is selected. Go to Raster Layer, Data, Create Chart, and Histogram. In Chart Properties, be sure that Show Normal Distribution, Mean, Median, and Standard Deviation are all checked. Choose Band 5 for the variable from the drop-down list. This distribution shows that our forest training sample pixel values have a normal distribution in Band 5. Do the same thing for each band that is significant for the feature. For forest, we also checked Band 3, which is green visible. Now do this for the other classes, setting the band combinations that best displays that specific feature, and then looking at the histogram for those specific bands. You can see in my contents that I have created a separate clipped composite image for each of the training sample classes. I turned only these layers on. Let's look at agriculture's histogram for Band 5. Let's create the water histogram for Band 5. The distribution appears to be skewed to the left, but the majority of water pixel values are very low because clear, deep water absorbs and does not re-emit at most wavelengths. Examine each of the classes for normality in each of the significant bands. We state significant because for our 11-band Landsat 8 image, band 1 and bands 10 and 11 are not likely significant for our analysis. Determine if you need to add any training data to any of the classes. Now let's go to part 4, evaluating covariance between training samples.